Hello everyone, my name is Eloise. I am an early stage researcher at Monkey Bell Labs and a PhD student at the Universidade Pompeu Fabra. And today I'll be presenting our paper on the latency of IEEE 802.11 AX WLANs with parameterized spatial views. To give an overview about my presentation, I will start by introducing our problem statement and giving you some theory on the current special use techniques of IEEE 802.11 AX, as well as how does the baseline operation works and the operation with PSR. And then I'm going to summarize the motivation in our contributions. Second, I will talk about the performance evaluation of the parameterized spatial views that we performed. And finally, I will finish with some takeaways and some research directions on the topic. So we all know that Wi-Fi is basically everywhere. We have Wi-Fi in our houses, offices, industries, and one of the main reasons for this widely developed infrastructure is the simplicity of the IEEE 802.11 protocols, combined with the low-cost deployment and management. But there is one very critical issue with devices operating in the unlicensed spectrum that it's very, very critical when we're dealing with latency-sensitive applications, such as Industry 4.0 and autonomous robots. That is the mandatory listen before talk, LBT. So the listen before talk basically means that every device willing to access the channel needs to listen to the wireless medium before to ensure that there is no other ongoing transmissions before attempting to access the channel. So these can be a really showstopper for latency applications since it introduces important delays to these devices. A way of addressing this issue is actually by increasing spatial views, which means allowing more transmissions to occur concurrently. The current IEEE 802.11 AX protocol introduced two spatial use techniques. The first one is the Overlapping Basic Service Set Package Detect, or BSSPD, and the second one is the Parameterized Spatial Views, or PSR. The first technique basically consists on relaxing the signal detection threshold so that we can increase the probability of having concurrent transmissions. Whereas the second technique, the parameterized spatial views, consists on allowing or not spatial views to happen based on the potential interference that the stations can generate towards the AP holding the transmission. So parameterized spatial views is a very interesting technique for low latency applications since the AP is the one that controls the spatial views. And moreover, the next generation Wi-Fi, the IEEE 802.11be, is currently discussing how to further increase the worst case delays by building features on top of the PSR. And you should be wondering, but how does exactly this PSR work? And I'm going to answer to this question by giving you an example that highlights the relevance of the PSR for low latency applications. First, let's take a look of how is the baseline operation of the 11AX. So in this example here, we have two basic service sets, BSS1 and BSS2. The station in BSS1 is a broadband traffic station, and the two stations in BSS2 are stations with a low latency traffic, which in this example means that they have short packages that need to be delivered in a timely manner. So simplifying the way that it works, basically, AP1 is going to trigger the uplink transmission from station 11. So it sends a trigger frame telling the other stations that it is triggering this uplink transmission. Then station 21, station 22 from BSS2, they will receive this trigger frame and they will set their network allocation vectors, basically indicating for how long they will differ from channel access. That is exactly the duration, the duration of the uplink transmission from station 1 to AP1. So they differ from channel access during this transmission. And once the transmission is finished, they are both station 21 and station 22 are free for contending for channel access again. So in this example, station 21 is the first one to get channel access, so it transmits the data, and the other station waits until it's finished to transmit its own data. So, I mean, what we can see here is that like it is not very efficient for the low latency stations with these very small packages to have to wait this long transmission in the order of several milliseconds before they're actually able to transmit the packages. So this has very bad latency consequences for the low latency stations. But now, when we activate the PSR, the way it goes is, again, the AP1 is going to trigger the uplink transmission, but this time it's going to indicate in the trigger frame that it is allowing special use operations to happen. And together with this information, it is going to set a maximum interference level that can be perceived by the AP1 without having serious consequences for this ongoing transmission. And so the other two stations from BSS2, they will receive this trigger frame and they will see that special use operations are available. So they will check two conditions. The first condition is the trigger frame needs to be sent from another BSS. So in this example, this first condition is valid because the trigger frame was sent from an AP from BSS1. And the second condition is that the intended transmission power of these two stations cannot exceed the interference level that was set by AP1. Given that those two conditions are valid, then the two stations, the two low latency stations, proceed to transmit their packages under those power constraints. And the interesting thing here is that now they can deliver their small packages as soon as their packages arrive to the queue. And this, I mean, they do not need to wait for this long transmission to be finished, they are able to deliver their packages in the timely manner that they are expected to do so. Most of the works in the literature, though, focus on only surveying the functionalities of those two special use techniques, and there are some simulation-based performance evaluation for the OBSS PD, but there's no currently works on the literature characterizing the PSR performance. And this is because characterizing the PSR performance is actually very difficult, because for having an accurate analysis, we have to have some standardized features implemented, such as the trigger frame operations. And this is actually very complicated, and it's not implemented on any known simulator. So we did this, and our main contributions with this paper was a realistic analysis of the effect of the PSR, considering different scenario densities, traffic loads, AP antenna capability, and all this analysis was made based on detailed standard compliance system level simulations. The system configuration used for our simulations was basically this scenario here, with 3 Wi-Fi APs separated by a distance of t meters. And as PSR operates in uplink, we only have uplink traffic. In this scenario, we consider 24 stations, but very important information here is that we have 8 low latency traffic stations, and only those 8 low latency traffic stations have PSR capabilities. So the other 16 stations are broadband traffic stations, and they do not have PSR capabilities. We also use in our simulations a 3D spatial channel model, and the evaluations parameters were basically the deployment density, in which we vary this distance d. We also use different traffic loads, and we also vary the number of antennas in the APs. So for our first evaluation parameter, which is the deployment density, we varied the inter-AP distance from 10 to 20 to 30 meters. And what we can see here is that, like, if we observe those blue curves, which are the low latency stations with PSR capabilities, and those are the low latency stations with the black ones are the low latency stations without PSR capabilities, we can see that overall, the smaller delays are achieved when we have PSR activated, and we can go up to 3 to 8 times smaller delays when PSR is activated. Now, if we look at the behavior of the low latency stations in the baseline scenario, we can see that the higher the density of the scenario, the smaller the delays. And this happens because, in considering the baseline, as the stations are closer to the AP, they can transmit using higher MCS levels, and this has a positive impact in their performance, especially in the delays. But now, if we look at the performance of these low latency stations with PSR, we can see that actually the delay is reduced when we go from a very high density scenario to a medium density scenario. And this happens because we have in high density scenarios, we have actually less spatial reuse opportunities because the stations in those crowded scenarios very often do not satisfy the power constraints imposed by the donor AP, and or they might sense the medium as busy because of physical carrier sensing. But now, as the density decreases, so the farther the stations are from each other, we can see that the worst case delays are actually increased as this distance grows. And this is because as the baseline, for the same reason as the baseline scenarios, the performance loss for having those stations farther apart, it outweighs the gains that we have by activating PSR. For the second evaluation parameter, which is the traffic load, so we vary the offered traffic for the broadband stations, and we can see basically two things here. The first thing is that for low to moderate traffic loads, which is up to 20 megabps, the latencies for both spatial reuse activated or not are very similar, and this happens because, well, with low traffic, the medium is generally available, so there's no need for content for channel access for long periods. But as we increase the traffic load, we have a substantial latency decrease up to 4.6 times. So we have like this decrease in the latency of 4.6 times. And this shows us that with a more aggressive spatial reuse, we can have very, very important benefits for higher traffic loads. And finally, if we vary the number of antennas in the AP, so we vary it from 1 to 2 to 4 to 8 antennas in the APs. And what we can see here is that basically, first, the latencies are generally reduced as the number of antennas in the AP grows. So the more antennas, the better. And also, for all the cases, all the number of antennas, the PSR capable system always outperforms the corresponding baseline. And we can also observe that up to the 95th percentile, even like the single antenna APs can outperform the 8 antenna AP baseline. And this is very interesting because it shows that by simply allowing low latency stations to have a more aggressive channel access, we can have a better latencies than by increasing the number of antennas in the APs. So this is a possible alternative. So to wrap it up, the main takeaways from this presentation are that for all scenario densities, we saw that PSR can reduce the worst case latencies with respect to the baseline operation by a factor up to 3.8 times for medium density scenarios. We also saw that by allowing a more aggressive spatial reuse in high load scenarios, we can have remarkable latency benefits. And last, we saw that for this scenario that we considered, even one single antenna AP with PSR capabilities can outperform multi-antenna baseline APs. And this shows that PSR is a potential alternative for more costly multi-antenna AP, since by activating the feature, you can have very remarkable latency benefits. And some research direction are basically investigate how can we build features on top of the PSR framework, such as coordinated beamforming and null steering, in order to further increase spatial reuse and reduce latency. Here are some references. Thank you very much for your attention and stay safe.